We're going to briefly address the other component of the nonlinear perturbation pressure, that is, that which is coming from the fluid extension. That's going to be associated with a positive effect on perturbation pressure. So wherever we have the presence of compression or stretching in the atmosphere corresponding to either divergence or convergence, because we're squaring that to determine the perturbation pressure, that's going to result in a surplus of nonlinear fluid extension related perturbation pressure. So again, wherever we have stretching or compression in the atmosphere, this perturbation pressure nonlinear fluid extension term is going to be positive regardless of spin. So what this is going to do is that beneath the level of maximum updraft, where we have stretching occurring in the atmosphere, it's going to generate a positive perturbation pressure nonlinear fluid extension component in the lowest part of the atmosphere, which is going to enhance lifting beneath the incipient updraft peak, or any updraft peak, and this is going to be the source for buoyant parcels, thus mattering more so for vertical motion, whereas at the same time in the upper reaches of the profile, the compressional effects of the decreasing vertical motion with height above the level of maximum updraft will correspond to also a positive nonlinear fluid extension term that can suppress ascent to some degree above the updraft peak, although this is removed from where we have the source region for buoyant parcels and as an effect being superimposed by an already established updraft. So there's going to be potentially much more apparent role from the nonlinear process, from the fluid extension component that is, again, going to be related to squaring of this divergence component to determine the nonlinear fluid extension effect on enhancing updraft. So the nonlinear concept, where we have both the shear as well as fluid extension that are resulting in all of these dynamically driven enhancements to updrafts, much more so than what CAPE alone can provide us reason as to why supercells can be much more intense and longer lasting than pulse storms. They have an additional lifting from hydrodynamic perturbation pressure gradient forces. These are often arising from the interaction of the vertical shear with the updraft, and this is all very much encapsulated within the hodograph structure and the interaction of the updraft with the vertical shear profile as depicted by the hodograph. In fact, just some very rough numbers here. Combined dynamic lifting from a 1 millibar perturbation pressure difference over 1 kilometer is the same forcing as the buoyancy from a parcel's virtual temperature boost of 3 Celsius. Again, 1 millibar perturbation pressure difference over 1 kilometer is the same forcing, and again, that can be driven by all these updraft and shear effects as the same forcing as buoyancy from a virtual potential temperature boost of 3 Celsius. That just goes to show how much of a dynamical process is evolving outside from the vertical shear updraft effects, interactions, that go beyond just the thermodynamic component alone. All right, so we've talked extensively about the nonlinear component. Let's talk about the linear component. Remember, with the nonlinear component, we've addressed a lot about cell splitting. We haven't talked about whether the right of shear vector or the left of shear vector cell is going to be dominant, but we have addressed the concept of convective intensification, nonlinear, from shear effects, as well as fluid extension. So we're going to talk about the linear effect right now. We're going to have to appeal to the concept in vector analysis of a dot product. And the perturbation pressure linear effects are going to be proportional to the vertical shear of horizontal wind vector. We know what that is now. Yes, it's this partial derivative, but don't worry, those are just vectors along the hodograph, the chords along the hodograph, what's tangent to the hodograph. Again, hodograph determines that, dotted with the del operator, or gradient, operating on the updraft. So in other words, the gradient vector here, or operating on the vertical motion, what that effectively is we know the gradient vector is always pointed uphill, or towards the maximum value of a scalar quantity. So this is what we're going to call the updraft gradient vector. These are just vectors that are pointing towards the updraft. They're pointing uphill. They're pointing upslope. They're pointing of a particular scalar quantity. So if we look down, we're going to look down right now at the slide. We're going to look down at a map. We're going to look at a plan view here. This is some updraft. All of our updraft gradient vectors are all pointed toward the peak of that updraft. They're all pointed uphill. You can see wherever we go, they're symmetrically pointed uphill, all converging on that maximum updraft point there. And so that vector field, del W, is just sketched out over here, the updraft gradient vector. You can see that here. Now what happens when we take our westerly shear profile, as we talked about, that's this term over here, and we dot that with our updraft gradient vector? Well, wherever the westerly shear is parallel to our updraft gradient vector, we get a positive value, perpendicular, 0, anti-parallel, negative value. Well, what we see is that everywhere up shear of that incipient updraft, the westerly shear has a component that lies parallel to the updraft gradient vector. So the dot product is positive everywhere up shear, or to the west, of that initial updraft. It's going to be maximized where updraft gradient vector is completely parallel to the westerly shear vector, or along our west-east axis. And the entire thing is opposite in sign, SIGN, down shear. Everywhere down shear, our updraft gradient vector is anti-parallel, has an anti-parallel component to our westerly shear vector, maximizes in magnitude where the two are completely anti-parallel along the x-axis over here. And then along the y-axis over here, our westerly shear vector is everywhere perpendicular or orthogonal to our updraft gradient vector, resulting in no perturbation pressure from the linear effects. So everywhere up shear, we get positive linear perturbation pressure. Everywhere down shear, we get negative linear perturbation pressure. So let's now revisit what we've talked about for the case of the westerly shear vector. We're going to look down now at our updraft, and we're going to plot again each of these updraft gradient vectors, which are also called going to the updraft vectors, because they're all directed toward the updraft mound, as you can see here, and they all converge on the updraft. All of our shear vectors, which I'm going to show in bold here, are going to be from west to east, generating our up shear positive perturbation pressure, down shear negative perturbation pressure, 0 along our y-axis over here. And so where our shear vectors align with the going to the updraft vectors, we get positive linear perturbation pressure up shear, and then when they oppose, we have negative linear perturbation pressure down shear. So what is the effect of this westerly shear vector, where, again, our shear vector is westerly at every level in our convective updraft? So regardless of where we are, it's always of where we are in the convective updraft, it's always from the west. Well, we know that this effect is going to maximize where updraft is strongest. That's going to be where our updraft gradient vector is going to be having the strongest magnitude, and that's going to be in the middle parts of the updraft, middle to upper parts of the updraft. And so that's going to be the driving force for our induced vertical perturbation pressure gradient forces. So again, with our westerly shear profile, that's going to be resulting in up shear positive perturbation linear effects, and down shear negative linear perturbation pressure effects. those effects are going to, again, maximize at the level of maximum updraft, where that dot product is going to be maximized. And so where we have the maximum mid-level positive perturbation, linear perturbation pressure, well, where it accumulates in the mid-levels of the atmosphere compared to lower positive values near the ground, that drives a downward directed linear perturbation pressure gradient force. Whereas down shear, where we have the buildup of negative linear perturbation pressure in the mid-levels of the atmosphere, that's going to be more negative in the mid-levels than it is near the ground, so the perturbation pressure gradient force from linear effects is directed upward towards the lower perturbation pressure. So same thing, same idea. Up shear, it's directed downward because everything is positive and it's being directed towards lower but still positive linear perturbation pressure, whereas down shear, looking to the east, we have a negative perturbation pressure everywhere throughout the vertical profile, but it's more negative in the mid-levels, and so compared to the low levels, our direction towards decreasing linear perturbation pressure is upward, and that drives a down shear acceleration upward. So again, we've addressed the case where we have the same shear profile through the entire updraft layer. And what this does is it enhances upward motion on the down shear side of the updraft and suppresses upward motion on the upshear side of the updraft. And this is going to result in new cell development, propagation, down shear of the initial updraft. But again, we're going to really highlight here that this is talking about the case of the unidirectional shear profile. So we have the same, the component, the same shear direction exists at every level within the profile, within the convective updraft. So in general, for the updraft layer shear component that's everywhere in the same direction or out of the west, every single component of the shear vector has a westerly component, or every single shear vector has a westerly component in the updraft layer. For the updraft layer shear component that's everywhere in the same direction, the vertically varying updraft, which we say maximize the mid-levels, results in down shear linear perturbation pressure gradient force that's upward down shear, favoring down shear cell propagation. And this effectively just moves all components of the initial cell split within the unidirectional shear profile straight photograph down the shear vector, maintaining the cell symmetry. So again, what we talked about in that previous slide is where through the entire convective layer we had a component of the shear that had the same direction in every single level, westerly. Now we can have westerly shear be a consistent shear component through the entire updraft layer, yielding west to east propagation component of incipient and flanking updrafts. But what if, in addition to a component of our shear through the entire convective layer that's westerly, we also superimpose a southerly shear that reverses to northerly with height above ground? That's going to create a concavity in the photograph. So let's look at this over here. This is a photograph with an arch. Now, as you can see, through the deep layer, we have, if we connect 2 points to create a chord on the photograph from the low levels to the upper levels, we have westerly shear through deep layer. In fact, every single tangent to this photograph has a west to east shear component, a west to east tangent component. But in the lower part of the photograph, we also have a component of that tangent to the photograph, or a shear component, being southerly, and in the upper part of that photograph, a component of the tangent being northerly. So in addition, so we're superimposing everywhere our westerly shear with a reversing shear pattern across our deep shear vector. So again, our deep shear vector, west to east, there's a component of the shear at any infinitesimal layer within our hodograph that's west to east, but across that shear vector we have a component that reverses from the low levels to the high levels in the convective layer. So let's look at the process of determining the linear perturbation pressure sign in the lower part of that updraft. So in the lower part of the updraft, we're gonna only look at the component of the shear that varies from the low levels to the high levels across the consistent shear direction within the convective layer. Again, consistent shear direction is out of the west, that chord from the low levels to the high levels, that's consistent in direction in every single tangent within the hodograph. And you can see that in the lower part of the hodograph, where we have the component that's not consistent, that reverses from the low levels to high levels, where we have southerly low-level shear, we have that bold low-level shear vector. You can see all the bold low-level shear vectors everywhere in the area, whereas our updraft gradient vector, or our going to the updraft vector, are all shown in these thinner arrows you can see over here, resulting in positive perturbation pressure to the south and negative perturbation pressure to the north, or positive perturbation pressure in the lower part of the atmosphere to the right of the deep shear vector, or to the right of the consistent shear vector, and negative perturbation pressure, linear perturbation pressure, to the left of that deep shear vector, or to the left of the consistent shear vector. Now, because of the reversal of the meridional shear from the low levels to high levels, we get a different sign distribution for the upper part of the convective plume. While the going to the updraft vector is the same, has the same distribution, we now have northerly shear that's causing the dot product to switch signs across the x-axis. So now, to the left of our westerly deep shear consistent shear vector, we have positive perturbation, linear perturbation pressure, and negative to the right of our westerly consistent shear vector, deep shear vector. What does this look like? Now let's look at the XY plane going into the slide. Now up is looking at this updraft. Here's our updraft, an incipient updraft, or any updraft for that matter. And when it's superimposed on this shear profile, what that does, again, in the lower part of the profile, we get a positive linear perturbation pressure to the right of the westerly deep shear vector, westerly consistent shear vector, and negative to the north or to the left, that reverses with height above ground. And what that does is it induces a new updraft to the right of the deep shear, consistent westerly shear vector, and it induces subsidence to the left of that deep shear vector. This is what causes preferential or one particular deviant cell continuing to maintain its existence, whereas the other component of the split does not continue. It's the linear component that's associated with the reversal of the dot product between the low levels and the high levels from the reversal of the shear, in this case from the concavity. Again, the concavity is going to be associated with a reversal of shear component across a consistent deep layer shear component that's the same direction, has the same direction component at every tangent in the photograph. That's what gives the arch, or the bow, or the concavity here. So, looking down the photograph in this particular case, which is also the shear profile through the updraft layer, we will have down shear propagation in that direction. That is a component. Assuming our photograph doesn't loop around, we can identify an axis along which all shear vectors through the profile have a unique parallel component connecting ends of the photograph over the deeper shear vector. So what that means, again, we're just summarizing here what we just talked about. Here's our bowed-out photograph. We'll have a deep shear vector that goes from west to the east with vortex tubes that go from south to the north. By bowing out the photograph, we generate an alternating linear perturbation pressure pattern in the vertical profile, causing an updraft enhancement. And I repeat, it's very important here, an updraft enhancement to the right of the deeper shear vector, which is on the same side of the photograph with the concavity for this case. But we can generalize and say that there's an updraft enhancement to the right of the deeper shear vector on the same side of the photograph with the concavity. So in the case that we addressed earlier, with our consistent westerly shear, deeper shear profile that experienced an alternation in meridional shear from southerly to northerly, from the low levels to high levels, our favored updraft was to the right of the deeper shear vector, or inside or on the same side of the photograph where there's concavity, to the right, to the south, looking down the deep shear vector, and updraft suppression to the left of the deeper shear vector, or on the convex side. So we think of our consistent shear vector, deep shear vector from west to east, and we're going to have both a candidate to the right and to the left for new cells, new rotating updraft, cyclonic to the right, anticyclonic to the left. Well, the one that's going to win, the one that's going to be dominant, is going to be the one that's on the same side of that updraft as the side of the photograph with the concavity, and the one that's suppressed, the updraft suppressed, is the one that corresponds to the convex side of the photograph. So in addition to the linear enhancements that are causing the concave side of a photograph cell to be dominant, and all of the eventual dynamical considerations that result in further updraft intensification, that bowed-out photograph is also giving us some storm relativity to feed into the nonlinear effects. So in summary, for this particular case, the cell that will be dominant from experiencing the linear enhancement to the updraft from the linear perturbation pressure gradient force is going to be the one to the right of the deep shear vector, one to the right of that consistent westerly shear profile, resulting from the reversal of the meridional shear from the low levels to the high levels. In this case, we would have right deviant motion for the mesocyclone, and that's to the right of the incipient updraft relative to the deep shear vector. But to generalize here, that which is to the right of that incipient updraft, favoring the right dominant cell, is going to be the same in general terms as the side of the photograph as where we have the concavity looking down the deep shear. So given our arching photograph that we showed previously, looking down the deep shear, the side of that photograph with the concavity is to the right. So the updraft enhancement from linear effects is on the same side of the incipient updraft as the side of the photograph with the concavity looking down the deep shear vector. Whereas the updraft suppression is on the other side, or the convex side of the photograph, in more general terms. For our specific case, that would be to the left of the photograph that we had worked with previously, but in more general terms, the updraft suppression is on the convex side of the photograph looking down the deep shear vector. Again, that is going to be when considering where, relative to that incipient updraft, looking down the deep shear vector, we have the linear effect enhancing our perturbation upward motion from the linear perturbation pressure effect. So in summary, the interaction of an updraft with an environmental vertical wind shear is going to induce a cross shear, or along the arching vortex tube, resulting from the vorticity associated with the vertical shear of the horizontal wind through a deep layer or through some consistent shear layer, splitting rotating cells that result in nonlinear shear enhancements from perturbation pressure that initiates this positive feedback process, enhancing the flanking rotating cells from further vortex tube stretching, further being enhanced by the nonlinear fluid extension component. Storm relative helicity, streamwise vorticity, all play a role in terms of influencing the nonlinear shear component, for instance. Now, cells propagate down the hodograph, down that deep shear vector, down the consistent shear vector through the convective layer, owing to the linear perturbation component. The side of the hodograph with the concavity, which could be to the right or to the left of the consistent orientation shear vector, determines the upward linear perturbation pressure gradient force and the dominant cell, the one that is on the side of the hodograph corresponding to the convex portion is where we have the suppression take place of upward motion. And remember, storm relative helicity supports immediate updraft rotation, which can go into supporting nonlinear shear perturbation pressure enhancements.